Hello everyone. Today we are going to study about diode current equation. As we have studied about the VI characteristics of diode and that in that characteristics we have seen two regions, that is forward bias region and reverse bias region, and there we have seen the characteristics between V and I. That is, in forward bias region the characteristics was exponential, and in the reverse bias region the characteristic was linear. So, we have to seen the mathematical aspect of that also. So, that is defined by the diode current equation. So, the diode current equation expresses the relationship between the current flowing through the diode as a function of the voltage applied across it. So, it is nothing but the equation shows how the current varies when the voltage is applied across the diode. So, mathematically the diode current equation can be expressed as I is equal to I naught e to the power q v upon n k t minus 1. So, this is the diode equation which is applicable for the VI characteristics, or we can say that for the reverse bias condition as well as the forward biased condition. Now, in equation 1, I is the current flowing through the diode. It is the main current which is flowing, that is when in the forward bias condition this current is the actual rated current flowing through the diode, that is from anode to cathode, and when it is reverse bias, it is the amount of current flowing in the form of leakage current. I naught is the dark saturation current. We will discuss in detail about this in future. Next is Q. Q is the charge on the electron. V is the voltage applied across the diode. The amount of voltage which we are applying as the forward bias or as the reverse bias. So, the V is showing that the amount of voltage. N is the exponential ideality factor. K is the Boltzmann constant, and as we know the value of K is 1.38 into 10 to the power minus 23, and next is T. T is the absolute temperature in Kelvin. Here the factor K T divided by Q can be written as voltage term, or the in the form of a voltage which is a temperature dependent term. So, K T divided by Q can also be written as V T. Now, in the above expression shown in equation 1, the two factors or the two parameters are utmost important to understand. One is dark saturation current and second is the ideality factor. So, let us study something about the dark saturation current. It indicates the leakage current density flowing through the diode in the absence of light, hence dark. Hence, the word dark is used with this current. It is the amount of leakage current flowing through the diode. As we all know, during the forward bias condition or during the reverse bias condition, when the diode is not in a conductive mode, a smaller amount of current always flows, which is called as leakage current. So, this saturation current or dark saturation current indicates the leakage current density flowing through the diode in the absence of light or simply in the dark condition. So, this parameter is the characteristic of the diode under consideration, and it indicates the amount of recombination which occurs within it. That is, I naught will be larger for a diode in which a recombination rate is higher and vice versa. So, this parameter shows it is the characteristic of the diode which is under consideration, and it indicates the amount of recombination. So, I naught the value of I naught will be larger for a diode in which recombination rate is higher. So, the I naught value shows the recombination, it depends upon the recombination process. The dark saturation current is directly proportional to the absolute temperature, and it is inversely proportional to the material quality. So, these are the two factors, that is absolute temperature and second is the material quality on which the dark saturation current depends. It means that when the temperature changes or there is a change in temperature, as we have seen in the definition also, this is the value of current at the dark condition or when the light is not applied. So, definitely when the light is applied, the temperature gets changed. So, it is important factor on which the dark saturation current depends. And another factor in which it is inversely proportional to is the material quality. So, the amount of saturation current or the leakage current which is flowing in the material, it depends upon its quality. Next factor is the ideality factor. It indicates the nearness with which the considered diode behaves with respect to the ideal diode. Now, as we all know, any device or any component, it is having the working in the two zones. We can say that ideal zone and the practical zone. So, there are some conditions of diode in which is called as ideal condition, and the actual conditions are called as the practical conditions. So, the ideality factor shows how near the practical diode behaves like an ideal diode. So, if the diode under consideration behaves exactly as that of an ideal diode, then the value of ideality factor will be 1, but practically it will always be less than 1. It will never become 1, because if it becomes 1, then it is called as the ideal diode. Its value increases from 1 as the difference between the behaviors of the ideal diode under consideration increases. So, greater is the deviation, greater is the value of n or ideality factor. So, when the deviation is more, we will get the value of ideality factor more. The value of ideality factor is typically considered to be 1 for germanium diodes and 2 for silicon diodes. Exact value of ideality factor depends upon the following factors. So, as we have seen, this factor shows the nearness of the working of the diode as a ideal diode. So, definitely it will depend on certain factors. So, those factors are: first, electron drift. So, here electron drift, as we have studied in past, drift is the word associated with the minority charge carriers. So, in p-type material, electrons are the minority charge carriers. So, when the electron drifts from one region to another region, it affects the ideality factor of the diode. Second is diffusion. Diffusion is the movement of the majority charge carriers from one region to another region. So, when the diffusion process or the amount of diffusion changes, it changes the value of ideality factor. Next parameter is on which the ideality factor depend is the carrier recombination, which occurs within the depletion region. As we all know, in the depletion region, recombination process takes place when the biasing is applied. So, the carrier recombination which occurs within the depletion region also affects the value of ideality factor. Next factor is the doping level. As we have seen, the doping level or the amount of impurity also affects the working of diode. So, the doping level affects the ideality factor. So, it is also an important factor which is related to ideality factor. Next parameter is the manufacturing technique. When the diode is manufactured, there are certain techniques by which the diodes can be made. So, when the techniques are changed for different techniques, from different techniques, when the diodes are made, the diodes are having different ideality factor. And last is the purity of its material. So, the material which is selected for the manufacturing of diode, on this the ideality factor depends. So, as we all know, the pure materials are not used, some impurities are inserted or added to the pure material. So, amount of purity remains, on that the ideality factor depends. So, in forward bias condition, the bias voltage is considered positive and hence exponential index has positive sign. As we have seen in equation 1, when the voltage, forward voltage is applied. The bias voltage is positive, we have taken it as a positive voltage, it is up, its value will be positive. Hence, the exponential term, that is e to the power q v upon n k t will be greater than 1. That means its value is very much large than 1. So, what we can do here is that we can neglect 1 with respect to the exponential term. Therefore, for forward bias condition, the diode equation becomes I is equal to I naught into e to the power q v upon n k t. Here the current is having an exponential term, and that is why in VI characteristics we have seen in the first quadrant the characteristics obtained due to forward bias condition, the characteristic obtained is exponential in nature. So, the above equation indicates that once bias voltage exceeds cut in voltage, the forward current increases exponentially. There will be a large amount of current flow through the diode. So, once the barrier potential is overcome by the application of forward bias, the current starts to rise exponentially, and that is why the exponential characteristics is shown in the VI characteristics of diode in the first quadrant. In reverse bias condition, the bias voltage V is treated negative. Due to this, exponential index has negative sign. As we can see in equation 1, the exponential term is having the voltage V, which is the actual voltage applied in the diode. So, in the reverse bias condition, the polarity by which the diode is connected with the external source is opposite in direction. That means, the positive terminal of voltage source is connected to the negative terminal of diode, and the negative terminal of voltage source is connected to positive terminal of diode. So, the sign for the voltage source is negative. Hence, the whole exponential term, that is e to the power q v upon n k t, becomes negative, since negative sign comes with the v. So, the exponential terms becomes e to the power minus q v upon n k t. Now, this exponential term is negative and its value is very much less than I. That is why this value exponential terms can be neglected with respect to 1 with the figure 1 in equation 1. Hence, neglecting the exponential term, we get the current I is equal to minus I naught. So, the above equation shows that under reverse bias condition, the current is a reverse saturation current, which is negative, indicating that it flows in opposite direction to that of forward current and almost constant. Therefore, the current in the reverse bias direction is only the leakage current flowing through it, which is opposite in direction to the actual direction of the diode current, that is forward current, and it remains almost constant. And therefore, the current shown in the reverse bias condition, that is in the third quadrant, before the breakdown voltage arises, the characteristics is linear, since I is equal to minus I naught. So, both this explanation about the forward and reverse reverse condition for the current can be shown in this figure of VI characteristics of diode. So, in the first quadrant we can see that exponential characteristics shown for the forward current, and for the reverse current a linear curve is drawn having a small amount of magnitude, that is of I naught, which is the leakage current. So, the current equation shows that the diode current equation shows that in the forward direction, or when the forward bias is applied, after the knee voltage or the barrier potential is overcome, the current rises exponentially, and it is shown through an exponential curve. And in the reverse bias direction, when the reverse bias is applied, a small amount of leakage current flows and its characteristics is linear in nature. Since I naught is due to minority carriers generated due to thermal energy, and hence I naught is temperature dependent. As we have seen in the VI characteristics of diode, the current I naught is due to minority carriers, and these minority carriers are due to thermal energy. So, from here we can see that I naught is temperature dependent term. Next is voltage equivalent, that is Vt of temperature is KT upon Q, which can be written in equation 1. It is also a temperature dependent term. Hence, we can conclude that the forward current which depends on I naught and Vt is also a temperature dependent term, that is the current flowing through the diode, that is forward current I, is also a temperature dependent term. Hence, we can conclude that the entire VI characteristics of a PN junction diode depends on the temperature. Now, let us study about the resistance of diode. As we know, in a diode, when the two types of biasings are applied, two different type of resistance are offered by the diode. So, from that there are two types of resistances, that is forward resistance and reverse resistance. So, first we will study about the forward resistance. So, the forward resistance is the resistance offered by the diode to forward bias condition, and it is known as forward resistance. So, this resistance is different for both alternating and direct current. Now, this point is very important to understand, that the resistance offered by diode during forward bias condition is different for the two types of signals, that is current signals, that is AC and DC. So, on the basis of this, the forward resistances are of two types, that is DC forward resistance and AC forward resistance. So, when the diode is working on the forward bias condition, it is offering a resistance which is called as forward resistance, and this forward resistance is of two types, that is DC forward resistance and AC forward resistance, and this type comes on the basis of the signals, that is direct current, that is a type of current, that is a direct current or alternating current. So, this figure shows the current in the forward direction mode, or we can say that forward bias condition. Here different voltages are shown, that is OA, OB and OC, and different currents are shown, that is OD, OE and OF. So, when the DC current DC voltage is applied at a certain amount of voltage, since we know the DC is a constant voltage, it is not in a pulsating manner, it is a constant or a stationary form of nature, it is having a stationary form of nature. So, for a particular voltage we will get a particular amount of current only, and it is not alternating in nature. So, suppose in this manner, suppose OB is the DC voltage. So, for that OB we are getting the amount of current is as OE, and when the current is applied, that is AC current is applied, AC current is alternating current, that is its magnitude changes with respect to time. So, when the amount of voltage changes with respect to time, so the amount of current will also change. So, here we are showing three different type of currents, that is OA, OB and OC for AC, and with respect to that three different types of currents are obtained, that is OD, OE and OF. So, let us study in detail about this DC forward resistance and AC forward resistance, and let us see how this can be calculated from the VI characteristic. DC forward resistance, it is also called as static resistance. Now, why this is called as static resistance? Since the DC is having a constant characteristic, or we can say that it is shown by a straight line, or we can say that it is static in nature, that is why the resistance obtained by DC is called as static resistance. So, it is the opposition offered by the diode to the DC current. So, it is measured by the ratio of DC voltage across the diode to the resulting DC current through it. So, as we have seen in the earlier figure, it is obtained from the value of DC voltage and DC current. So, from the above figure we can see that the forward voltage is suppose OB. So, with respect to that OB, the forward current will be OE. So, therefore, the DC forward resistance, which is denoted by capital R and in suffix F is denoted. So, RF will be equal to OB divided by OE, that is the ratio of DC voltage across the diode to the resulting DC current through it. Now, what is AC forward resistance? AC forward resistance is also called as dynamic resistance. Now, it is called as dynamic resistance because the AC is fluctuating in nature, or it is alternating in nature by its name. With respect to time, its value gets changed. That is why the resistance obtained by AC is called as the dynamic resistance. Now, what is AC forward resistance? It is the opposition offered by the diode to the changing forward current. That means, it is measured by the ratio of change in voltage across the diode to the resulting change in current through it. That is, AC forward resistance can be obtained as small r f, and it is equal to change in voltage across diode divided by corresponding change in current through the diode. So, as we have seen in the characteristics of the diode, VI characteristics of the diode, when AC current flows, there is a change in voltage with respect to time. So, that change in voltage is taken in the numerator, and with respect to that voltage the current also gets changed. So, corresponding change in current is taken in the denominator. So, from the figure, if P is the operating point at any instant, then forward voltage is OB and forward current is OE. To find the AC forward resistance, vary the forward voltage on both sides of the operating point equally as shown in figure above. Here AB is equal to BC. For forward voltage OA, circuit current is OE, and for forward voltage OC, circuit current is OF. That means, to obtain a AC resistance of a diode, suppose we are selecting a operating point as P. For that the voltage is OB, and with respect to that current is OE. So, for that to obtain the AC resistance, we are moving the voltage forward and backward. We are taking a value in the higher side and the lower side. Similarly, we are measuring the current in the upper side and the lower side. So, AC forward resistance is obtained as RF equal to change in forward voltage divided by change in forward current. So, RF will be equal to del V divided by del I, or from the figure we can see that del V is OC minus OA and del I is OF minus OD. So, from this we can obtain that the change in voltage is AC divided by DF. So, the forward resistance of a crystal diode is very small, ranging from 1 to 25 ohms. So, in this way we can obtain the forward resistance in the diode. Now, second resistance is the reverse resistance. The resistance offered by the diode to the reverse bias is known as reverse resistance. It can be AC or DC resistance depending upon the type of supply. So, like the forward resistance, reverse resistance can again be of two type, AC resistance or DC resistance. Ideally, the reverse resistance of a diode is infinite. Practically, this resistance is not infinite because a small amount of leakage current always flows for any value of reverse bias. As we know, for ideal cases the value of resistance is infinite for a diode, but as we see practically a small amount of leakage current flows. So, the resistance will not remain infinite, we will get a certain amount of resistance in the reverse bias condition. So, the reverse resistance is very large compared to forward resistance. In germanium diodes, a ratio of reverse to forward resistance is 40,000 is to 1, whereas in silicon diodes a ratio of reverse to forward resistance is 10 lakh is to 1. Now, let us see about the equivalent circuit of diode. The diode can have the 3 different types of circuits. First is ideal model, or we can say that circuit or model. First is ideal model, second is simplified model, and third is the approximate model. And so, the diode can be explained in these 3 modes or through these 3 models. As we have studied, in the ideal case, the diode is having 0 resistance in the forward bias condition and infinite resistance in the reverse bias condition. So, by that the VI characteristics become such that we will get a very straight line in the current axis for the forward bias and will not get any current in the reverse bias. So, this is the ideal condition. In simplified mode, we can add the amount of voltage, that is the actual voltage which is occurring at the as a barrier potential, that is shown in the VI characteristics, and it is also called as knee voltage. So, in the practical diodes or in the simplified model of the diode, the potential which is obtained at the barrier is shown in the VI characteristics, and the more approximate model is considered for the diode. In this, with the ideal diode, the barrier potential is considered as well as resistances are considered, whether it is the forward resistance or the reverse resistance. So, the circuit which is having the ideal diode with the barrier potential plus the resistance, actual resistance of the diode, that is forward resistance of the diode, it will show the approximate model of diode. In this, we can see the VI characteristics is showing in the forward bias region a characteristic of exponential nature. So, for a particular instant of time, the diode will be non-conductive, and when the knee voltage is overcome, that is the amount of voltage here shown is V naught. Beyond that, the diode becomes conductive and current starts flowing in the exponential nature. So, in approximate equivalent circuit, it consists of a switch in series with a battery V naught and internal resistance RF. So, to draw an equivalent circuit of a approximate equivalent circuit of a diode, we take a switch in series with a battery V naught and internal resistance RF with the battery in series. So, this shows the approximate equivalent circuit. Now, in simplified equivalent circuit, the internal resistance RF can be ignored in comparison to other elements in the equivalent circuit. Since we have seen the internal resistance RF, its value is very less compared to the reverse resistance. Therefore, in simplified equivalent circuit, this resistance can be neglected or ignored compared to the other resistance in the equivalent circuit or other elements in the equivalent circuit. So, it simply consists of a switch in series with a battery V naught. And at last, ideal diode or the ideal model of a diode. An ideal diode is one which behaves as perfect conductor in forward bias and as a perfect insulator in reverse bias. That means, ideal diode shows a forward resistance of the value 0 and it shows the infinite resistance in the reverse bias condition. So, forward resistance RF and potential barrier voltage V naught or the by which the battery voltage V naught which we are showing, they are considered negligible for the ideal diode, and to show the ideal diode only a switch is shown for the analysis. Thank you.